Here we have the graph of a cubic function f of x. We can see that it cuts the x-axis at -3, -1 and +2. Now we can get the factors of this function by using the three roots or solutions. You know, we're given that f of -3 is equal to 0. Okay, so by the factor theorem, x plus 3 is a factor of f of x. Similarly, f of -1 is 0, so you know we have that x plus 1 is a factor of f of x. Finally, we're given that 2 is a solution or root, so that means that x minus 2 is a factor. So we found three factors: x plus 3, x plus 1 and x minus 2. So if we multiply these three factors together, we get a cubic. But how do we know that that cubic is this one here? You know, it's quite possible that we need a number in front of this, like 4. You know, we have the three factors in x, the three linear factors in x, but it's possible that we still have a constant here. Technically, this constant is a factor, but it doesn't come out of the factor theorem. Okay, the factor theorem gives us linear factors. That is, factors that are linear in x. Okay, constants are not included. You know, so for example, if we were trying to solve this equation, we just divide across by 4, and it's like the 4 doesn't exist. And then, you know, we get our three roots by setting each of the three factors equal to 0. So it would not matter whether we have a 4 here in front if we're trying to find those three roots. You know, we could have a 2 or any number in front here. And if we're solving the equation f of x equals 0, we get those three roots: -3, -1 and +2. What we can do is look ahead and see that f of x has got a 1 in front of x cubed. So that means we have to have a 1 here. You know, because we're going to get x by x by x, which is x cubed. So we know that we just have 1 out here in front. We're also given the intercept. So from that intercept we can see that this is the correct expression. You know, if we let x equal 0, these three terms disappear, and this constant term in our cubic is the y-intercept. The graph of the function g of x equals -2x minus 6 intersects the graph of the function f of x above. So what we want to do is find those points of intersection. Now, at the points of intersection, the values of both functions are the same. What I mean is that at the x values of those points of intersection, the y values are the same. So the y values are given by f of x and g of x. So we have to find those values of x that make the y values the same, that make f of x equal to g of x. So we put f of x equal to g of x, and we solve the resulting equation to find those values of x. Now, if we do that, you can see that we get a cubic equation with no constant term. See, the constant term here is 0, and that means we can easily solve this cubic equation, because we can factorize x out of the left hand side. We don't have to try and guess solutions, because, you know, in other questions cubic equations involve some guesswork, because the cubic equations in other situations are set up so that one of the roots is a number like +1 or -1 or +2. So here we don't have to, you know, set up or try different roots to see what a root is and then use the factor theorem to break this down further. We can just simply factorize x out of this, and we get a quadratic which can be factorized into two linear factors. The product of these three factors is 0. That only happens if one of them is 0. So it could happen if x is 0, so x is a factor. If x is 0, all of this is 0. Or if x minus 1 is 0, then the whole lot is going to be 0. If x minus 1 is 0, then x is 1. If x plus 3 is 0, well, everything here will be 0. So that happens when x is minus 3. So for these values of x, both functions have the same value. F of x equals g of x. So these are the x values of the points of intersection of the line and the curve. So to find the y values, we just plug each of these values in turn into either f of x or g of x. Well, it's easier to plug them into this. So, for example, when x is 0, g of 0 is minus 2 times 0 minus 6, which is minus 6. G of 1 is minus 2 times 1, which is minus 2 minus 6, giving minus 8. And similarly for the third point. So there we have the 3 points of intersection. Here we have a question involving differentiation from first principles. Now I've covered several examples of this before, so I won't go through this. I'll just point out some of the main facts. We have to calculate this quotient here. H is some very small number. And we just calculate that by straightforward subbing in and simple algebra. And as I've explained before, this thing here is the slope of a secant to the curve. So I won't go through that picture, but if you take the limit as h approaches 0, the secant becomes a tangent to the curve. So we're getting the slope of a tangent to the curve at x, at a general value x. The secant passes through the point at x and a nearby point whose x coordinate is x plus h. Okay, that's a nearby point on the curve. So if you want to see that, I've covered that in detail and the geometry of what's going on. So anyway, here's the slope of the curve, which is also the same as the slope of the tangent to the curve, because if we zoom in on the point where the tangent meets the tangent and the curve become indistinguishable. So the slopes are the same. Here we have the function f of x equals 2x over x plus 2. And we want the coordinates of the points at which the slope of the tangent to the curve is a quarter. Now the question could have said find the coordinates of the points at which the slope of the curve. You don't have to say the slope of the tangent to the curve. Because again, as I've explained before several times now, you know, if you have some curve, well, if we take the tangent to the curve at this point, both curve and tangent are indistinguishable if we zoom in close enough on this point. So the slope of the tangent is the same as the slope of the curve at this point. Now the slope of a curve is the derivative of the curve. So 4 over x plus 2 squared is the slope of the curve at any point x. Okay, so we have to use the quotient rule to differentiate this here. And I've explained that many times before. It's got the form u over v, where both u and v are functions of x. And the derivative is v du dx minus u times dv dx, all divided by v squared. However, we're given that the slope of the curve is a quarter. So the slope of the curve is the derivative. We put the derivative equal to 1/4. We want to find the values of x. So we have a single fraction on either side, so we can just cross multiply. To find out what the x's are, we can take the square root of both sides of this. So if x plus 2 squared is 16, it means that x plus 2 is the square root of 16. Okay, to go from x plus 2 squared to x plus 2, we get the square root of 16, but that's got two values. It could be plus 4 or minus 4. So x plus 2 could equal plus 4, or x plus 2 could equal minus 4, because plus 4 squared is 16 and minus 4 squared is 16. If x plus 2 is plus 4, we get x equals 2. If x plus 2 is minus 4, we get x equals minus 6. So these are the two x values of the points on the curve for which the slope of a tangent is a quarter. Or you could say they're the x values of the points on the curve for which the slope of the curve is a quarter. Now this other way of doing it is pointless. This is just the same equation here. You know, you've squared out x plus 2 and got your quadratic into standard form, which means 0 on the right hand side, and solve it this way. But there's no need to do this, because when the quadratic is in this form over here, it's easy to solve. You just get the square root of 16. Expanding it out is just making things more complicated. So after finding x values of the points, we need the y values. So we're interested in 2 points on the curve. So they've got to satisfy the equation of the curve. So here's the formula that gives us y values of points on the curve. So we plug in the 2 x values that we got, and we get the corresponding y values. So when x is minus 6, y is 3. When x is plus 2, y is 1. So here are the 2 points on the curve where the slope of the curve is 1/4. Here's a graph of the function. So the function consists of these 2 curves, and you can see the points for which the slope of the tangent is 1/4. So you can see that for this tangent here, if we pick a point on it, say this point here, the point of contact of the tangent to the curve, increase x by 1. Because the slope is 1/4, we have to go up a distance of 1/4 to meet this line. Okay, so it's got a positive slope. And similarly over here at the point 2, 1, the slope of the curve is 1/4. Here we have to integrate a cos function. Now you can look up the integral of the cos function. You'll see that it's sine of x plus some arbitrary constant c. It turns out that the integral of cos of a times x, where a is just some constant, is 1 over a times sine of ax plus c. Now you can easily verify this by differentiating this function with respect to x. Or, if you like, you could do integration by substitution on cos ax to prove that it's given by this. Now the 5 is just a multiplicative constant. Just multiply by cos 3x, so that can be pulled out. So what do we have here? The integral of cos 3x is 1 over 3 cos 3x. We just apply this here with a equal to 3. So we get 5 times 1 over 3 sine 3x, and we have our constant. Of course, the 5 times 1/3 is just 5/3. The slope of a tangent to the curve y equals f of x at each point x of y is 2x minus 2. Now the slope of a tangent to a curve is just the same as the slope of the curve, which is given by dy dx, or, if you like, f prime of x. So this is the slope of the curve at any value x, and here it is 2x minus 2. Now we can actually treat this thing like a fraction and rewrite this as dy equals 2x minus 2 times dx. Okay, multiplying both sides by dx. And we can then go and integrate both sides. So we do that to find out what y is. So we have to work backwards here to find out what y is. Okay, we're given the slope of the curve. What is the equation of the curve? Well, if we integrate dy, we just get y. That's like integrating 1 with respect to y. The integral of 1 with respect to y is just 1y. And we get a constant. But we can shift that constant over onto the right side and combine it with the constant on the right side. I just call that constant c. So anyway, let's integrate 2x minus 2 with respect to x. So we add 1 onto the power to get x squared, and we divide by that new power. Now we have this multiplicative constant 2 in front here, so we just leave that in front. So we get 2 over 2x squared when we integrate 2x, but 2 over 2 is just 1. When we integrate minus 2 with respect to x, we get minus 2x, because the derivative of minus 2x is minus 2, and we get a constant. So the constant c here is a combination of the constant on the left hand side and the constant on the right hand side. So you know, if we had a constant here called a, and if we had a constant on the right hand side called b, we'd bring the a over, we get b minus a and call it c. You know, so we can just have the constant on right hand side. We don't have to have a constant written on both sides, because they can combine into a single constant. So this here is the equation of the curve. But we need more information. Just knowing the slope of the curve at every point isn't enough. I'll get back to that point later when I finish this question. The extra information here is a point on the curve. That's all we need actually, just one point on the curve. So we can see that when x is minus 2, y is 0. Okay, so we let y equal 0. Let x equal minus 2. Okay, so we're plugging this point minus 2, 0 into the equation. And it's got to satisfy the equation because it's a point on this curve. So that enables us to find out what c is. Solving this for c, we get that c is minus 8. So there's the equation of the curve. You know, without knowing this extra information, we would just have an arbitrary constant c at the end here. And in that case, well, all our curves are quadratics. They would cut at c. Okay, but we could have lots of functions. We could just change that value of c, and we could just raise the graph up and down, and the slope at any point wouldn't change. So the slope of this point is the same as the slope of this point up here, you know, on the same type of curve, just by changing the value of c. But you know, we just want one particular curve, the curve that passes through the point minus 2, 0. Now we're going to find the average value of this function over the interval 0 to 3. So this is just like the idea of the average value of a set of numbers. We add up all the numbers and divide by the number of numbers. So here we add up all the values of the function from x equals 0 to 3. So at 0 the value is minus 8. At, you know, 0.1 we have another value, it's actually negative, and so on. So adding up all the values of the function from x equals 0 to 3 means getting the area of this region here. Well, and it's going to come out to be negative, as you can see, because the value of the function for x between 0 and 3 is negative. So we have to integrate the function from 0 to 3, and then we have to divide by the number of values. Well, that's just the length of this interval here, which is 3 minus 0. So when we're averaging a function over an interval, we have to integrate the function over that interval, in this case the interval 0 to 3, and divide by the length of that interval. Okay, so the distance from here to here is 3. Okay, to integrate x squared, we add 1 onto 2 to get 3 and divide by 3. Integrating this, add 1 onto 1 to get 2, divide by 2 to get 1 in front. And integrate minus 8 to get minus 8x. And our limits are from 0 to 3. And we have to divide all of this by 3. So we've covered this before. You plug your upper limit in, work it out, then minus this expression with 0 in. You get that value, divide by 3. The answer to that is minus 8. ADEC is a rectangle with AC equal to 7 meters. AD is 2 meters. B is a point on AC such that AB is 5 meters. P is a point on DE such that DP is x meters. So by the way, that tells us that the distance of P to E is 7 minus x. Okay, the total distance DE is 7. F of x is PA squared plus PB squared plus PC squared, and we have to work out what f of x is. Well, we want to get PA squared in terms of x. Well, you can see that we have a right angle triangle here. So PA is the hypotenuse, so the square of the hypotenuse is the sum of the squares of the other two sides. That's 2 squared plus x squared. 4 plus x squared. PC squared is done in a similar way. We have a right angle triangle here. This side is 2. So the square of the hypotenuse, that's PC squared, is the sum of the squares of the two short sides. So that's 2 squared, which is 4, plus 7 minus x squared. So we have to square this side here, which is 7 minus x. Now minus x squared is plus x squared. Minus x by 7 is minus 7x doubled is minus 14x. We get 49 plus 4 is 53. Now what about pb squared? This is less obvious. Well, again we can take pb squared as square the hypotenuse of this right angle triangle here. So what are the two short sides? Well, this side is obviously 2. This side is the same as the side of rectangle. What's the distance from here to here? Well, we have the distance of p to e at 7 minus x. And we have the distance of b to c, which is 2 meters. So it's 7 minus x minus 2. 7 minus x minus 2 is 5 minus x. Okay, and if you check this, if you add 5 minus x onto 2, you get 7 minus x. The distance of here to here is 7 minus x, the same as from here to here. So the square of PB, that's the square of the hypotenuse of this right angled triangle, is the sum of the squares of the short sides. 2 squared is 4, and we have 5 minus x squared. Well, if we square that out, we get 25 minus 10x plus x squared. So simplifying, we get x squared minus 10x plus 29. Now we want f of x, which is the sum of those three quantities. So if you sum them, you get 3x squared minus 24x plus 86. F of x has a minimum at x equals k, so we want to find that value. Okay, the minimum, the value of x that minimizes the function. Now the easiest way to do that is to put the derivative equal to 0. So at the minimum, at the value of x that minimizes the function, the slope of the curve, or the slope of the tangent to the curve, is 0. So we put this derivative equal to 0. Well, what is the derivative? It's 6x minus 24. So we put the derivative equal to 0 and we get x equals 4. So at x equals 4, the slope of the curve is 0, which means that the curve has a minimum or a maximum value, or maybe a saddle point. Now it's clear, by the way, that we're dealing with a quadratic, so there's only one turning point. X squared term is positive, you know, so at x equals 4 we have a minimum. Okay, the x squared term is positive, so this is the shape that the curve has. So we're dealing with a minimum rather than a maximum. You can see that at x equals 4 the slope of the curve is 0. We have a horizontal tangent here. Before finishing this, I just want to briefly mention an alternative way to get the minimum of this function here. Now this way is more complicated, but it's worth knowing about. We can factorize 3 out of this expression, and we can then go and complete the square of this quadratic inside the brackets here. So that involves halving the coefficient of minus 8. The coefficient of minus 8 is minus 4. Then we square it to get plus 16. Now the reason we do that is because we want to get a quadratic which is a perfect square, which can be written as something squared, and you can see it can be written as x minus 4 squared. Okay, and you can easily verify that. So just to repeat that, we have the coefficient of x to get minus 4, and we square minus 4 to get plus 16. Now if we put plus 16 here, so we add in this plus 16, but we must compensate by putting a number here such that 16 plus 38 over 3 gives us 86 over 3. Okay, yeah, so 38 over 3 is what we need. Now you can see that if x equals 4, this thing is going to be 0. We're going to get 0 squared, which is 0. And that's the smallest value that all of this expression can have. You know, if we take any other value for x, positive or negative, we're going to get something, after squaring, we will get something that's positive. We'll get something positive added onto 38 over 3. So if x is some number other than 4, what we get inside the brackets, square brackets here, will be greater than 38 over 3. Okay, that's a complicated way to do it really, so in general you'd probably do it by differentiation. So anyway, we found that at x equals 4, our function has a minimum value. So, there's only one solution to this, so we don't have to decide is this a maximum or a minimum turning point. Now, we want to find the minimum value of the function. That's this value here. So we just plug 4 into the function. So we want the coordinates of this point, basically. We want the y value of this point. It's a point on the curve, so it satisfies the equation of the curve. So if we plug 4 into this, we get 38. Here we have the graph of the arch of a bridge, which is in the shape of a parabola. So we're given the length of the span, which is 48 meters. And we're also given the equation of the parabola. So here it is. And we want to find the coordinates of C, the highest point of the arch. So we have these 2 points on the curve, 0, 0 and 48, 0. So those are the points where the parabola crosses the x-axis. Now there are 2 ways we can find the coordinates of point C. One way is to differentiate. Well, you can see the answer is shown here is 24, but anyway, we differentiate and we set the derivative equal to 0, because as we've seen before, at a maximum or a minimum point, the tangent is horizontal, so the slope of the curve is horizontal. Okay, the slope of the curve is the derivative, so the slope of the curve is 0. And we solve that simple equation to get 24. Of course, a much easier way is to recognize that this point here, the x coordinate of C, is midway between the 2 roots. So it's midway between 0 and 48. To get the y coordinate, of course, we plug that value of x, which is 24, into the equation of the curve. So we want to get this point on the curve. So we plug 24 in for x to get 7.488. The perpendicular distance between the walking deck DE and AB is 5 meters. So we want the coordinates of D and E. Okay, so here is our diagram. So this horizontal line is 5 meters above our x-axis. So we have the y value of D and the y value of E. It's 5. So, we just let y equal 5 and solve the resulting quadratic equation. So we could write down that the equation of that horizontal line is y equals 5. That's the equation of any horizontal line. All the y values on the horizontal line are constant. So anyway, here's the parabola. So we just set y equal to 5, find the values of x that give y equal to 5. So we get this into standard form by having 0 on the right hand side. Note what A, B and C are, plug them in, and we can get the x values of those 2 points. Now we want to get the area of this shaded region here. So we can divide that shaded region into 3 parts. The first part is the area under the curve from 0 to 10, the x value of this point. So that's just integrating the curve, well, it's just called y here, from 0 to 10. We also need the area of this rectangle. So this runs from 10 to 38, the x value of this point. And the x value of B is 48. So the area of the last part is the integral from 38 to 48 of our function y. We can write that in later. Notice, however, that these 2 areas are the same by symmetry. So if we get the area from under the curve from 0 to 10 and double it, we'll have the sum of these 2 areas that I've just indicated. So we don't have to go doing this integral here. We can just do this one and multiply by 2. So here's y, and we need to integrate this. That's a straightforward integral. I won't go through that. Okay, what about the area of the rectangle? Well, one side of it is just 38 minus 10, which is 28. and this side here is just the y value of this point, which is 5. So it's 5 times 28, which is 140. Next we will write the equation of the parabola in part A in this form here. So k, p and h are constants. We want to write our parabola in a form where we have just 1x minus some constant all squared. So that suggests that we have to factorize out minus 0.013 so that we get a 1x squared here. Okay, to match up with this 1 here. Of course, when we square this x, we get the x squared that you see here. Okay, so that's the first step, to factorize out minus 0.013, and we have to have minus 48 here to give us plus 0.624 times x. Next we do a process of completing the square. So I briefly explained this earlier. We halve the coefficient of x, so we get half of minus 48, which is minus 24. And what we do is we square minus 24, because if we do that, we can write all of this thing as a square. We can actually write it as x minus 24 squared, and that's very easy to verify. If we square x, we get x squared. Multiply x by minus 24 and double, we get our minus 48. And if we square the minus 24, well, we just get this term here. So just to repeat that process, we look at the coefficient of x and half it to get minus 24, and we square the result. So what we've done is we've added in this extra term here. But if we add in this term, we have to compensate by subtracting it. Okay? Because after all, we must end up with x squared minus 48x. Right. So anyway, we write all of this as x minus 24 all squared, and that's multiplied by minus 0.013, and we also multiply the minus 0.013 by the term over here, of course, to get 7.488. So you see we're nearly there. This is our p in front of the bracket, x minus h is 24, as you can see. And this term here can be brought over to the other side, and it's called k. So now we have our equation in the form y minus k equals p times x minus h squared. So notice that this term here is the coefficient of x squared. The coordinates of the maximum point are 24, 7.488. That's what I'm showing over here. So why do these highlighted values in green give us the coordinates of the maximum point? Well, that's easy to show if we just let x equal 24. So we get y minus 7.488 equals, well, we have this number here, minus 0.013, multiplied by 24 minus 24. So this number is multiplied by 0, so we get 0. Well, that doesn't tell us that this point is a maximum, but it tells us that when x is 24, y is 7.488. The reason it's a maximum is if we go back up to this line here, we can see that this thing inside the brackets is always positive because it's something squared. It doesn't matter what x is. X minus 24 all squared is going to be positive. And then we're multiplying by something negative, minus 0.013. So overall, if I just highlight this here, we see that this quantity here is always going to be negative. It's going to be negative for all values of x. So we have a negative quantity plus 7.488. So that tells us that all of this expression here is less than, well, it could be less than or equal to 7.488. because it's 7.488 with this negative quantity, which will, obviously give us something less than 7.488. If this thing is 0, of course, we'll get exactly 7.488. And this thing in red will be 0 when x is 24. So that tells us that the maximum value of y is 7.488. So we can use that information to answer this part here. The coefficient of x squared is -2, and the coordinates of the maximum point are 3, -4. So the x coordinate of the maximum point appears here, and the y coordinate appears over here. Well, you can see the answer here, but I'll just go through it again. So we have y minus the y coordinate of the maximum point. So it's y minus -4, that's y plus 4, equals p, which is the coefficient of x squared. I've pointed that out already. And the coefficient of x squared here is -2. And we want it in this form here, so we have a bracket times x minus the x coordinate of the maximum, which is 3. Okay, so that's now in the form y minus k equals